Swayam Prabha. Digital India. Educated India.
Hello and welcome. Let us do some mathematics and learn the concept of operators. Suppose y of t is a signal or a function of time. Whenever we write ddt of y, we do not mean multiplication of y with ddt. Rather, the symbol ddt is the symbol of a differentiation operator. An operator is a mathematical object that acts on any signal like yt and produces another signal, in this case the time derivative of y. If you consider this ddt or time derivative operator, when it acts on sine omega t, it will produce cosine omega t. If it acts on t square, it will produce 2t. In general, if it acts on the signal yt, it will produce the time derivative of that signal. That means operators are functions of functions or functions of signals. In other words, an operator maps signals to other signals. Another example of operator is multiplication by 2 operator. This operator, if it acts on sine omega t, it will produce 2 times sine omega t. If it acts on t square, it will produce 2t square. In general, if it acts on yt, it will produce 2 times yt. Now we can combine different operators to produce or get new operators. For example, let us combine the time derivative operator ddt with multiplication by 2 operator in the following way. We shall take a signal yt and operate it with the derivative operator to get y dot t, and then we shall operate the result with the multiplication by 2 operator to get finally 2y dot t. Now this combination of the 2 operators can be written in a compact way like this: 2 ddt, which will take yt, act on yt, and will produce 2y dot t. Another example of combining operators could be like this. Take the time derivative operator and combine it with another time derivative operator such that we can start with a signal yt. The first operator will act on yt to produce y dot t, and then the second operator will act on y dot t to produce y double dot t, or the second derivative. Now these 2 operators together can be written in a compact form like this: d2 dt2, that is the second derivative operator, which acts on a signal y to produce the second derivative y double dot. Now, another example of combining operators is like this. You take the time derivative operator and say the multiplication by 2 operator in parallel, so that the signal yt goes to the time derivative operator and produces y dot. The signal y also goes to multiplication operator and produces 2y, and then we shall add these two together to get the final result, which is y dot plus 2y. Now this combination of the two operators can be written in a compact way like this: ddt plus 2. So y goes in and d dy dt plus 2y comes out. Now look at the fourth example of combining operators. This time we shall take the operator ddt plus 2, which we have discussed before, and we shall combine it with another operator, say ddt plus 3. We will combine them in cascade such that the signal yt is first operated or acted by ddt plus 2, and then we will get y dot plus 2y, and then the second operator will act on this result. So finally we shall get ddt plus 3 acting over this term y dot, that is dy dt plus 2y. So this will result in combine this ddt with dy dt to get d2 dt2 of y plus 3 multiplied by dy dt, then ddt of 2y, which means 2 dy dt, and finally 3 into 2y is 6y. So this is same as d2y dt2 plus 5 dy dt plus 6y. Now these two operators together can be written in a compact way like this: d2 dt2 plus 5 dy plus 5 ddt plus 6. So if y goes in, then d2y dt2 plus 5 dy dt plus 6y will come out. Now also note that this operator can also be written as in a product form like this: ddt plus 2 multiplied by ddt plus 3. Here it actually means that this operator and this operator will sequentially act one after other on the input signal. First, DDT plus 3 will act on Y, and then on the result DDT plus 2 will act to produce this term. Now here the order of these two operations does not matter. So you can operate DDT plus 2 first on Y. After that you operate DDT plus 3 on the result. If you do that, then also you shall get the same result. So here the order of operations, which one first, which one second, does not matter. Okay, now let us learn another thing. Consider this operator DDT minus A, where A is a constant. So that means this is multiplication by A operation. So if you give Y, you shall get dy dt or y dot minus ay. Now if you take y equal to say e to the power at, then the result of this operation will be 0. So let me write it: d dt minus a acting on this signal e to the power at will produce 0. Why? Let us expand. We shall get ddt of e to the power at minus a multiplied by e to the power at, and this is equal to 0 if you carry out this derivative. So this is one important thing to note. The next important thing is consider ddt minus a acting twice on a signal. And let me take this signal y as e to the power at as before. So this means we shall first operate e to the power at with ddt minus a, and then we shall apply this operation once again, and if you do this you shall definitely get 0. So this is second important thing to notice. The third important thing is this: if you apply this operator twice on the signal t e to the power at, that means you take t e to the power at and operate it with ddt minus a, and then again operate it with ddt minus a. If you carry out this operation twice, you shall get 0. I shall leave it as a homework that you prove it yourself. So this is third important observation. And now in general, if you take ddt minus a whole to the power n acting on e to the power at, you shall get 0. This actually means, as you know, operating the input signal n times with the same operation, n times, and you will get 0. Also, if you operate this ddt minus a to the power n on t to the power k e to the power at, where k is a integer, any integer like 0, 1, 2, any positive integer less than n, so up to n minus 1, then you shall again get 0. So this is the more or most general rule. If you take ddt minus a n times and operate it on t to the power k at, you shall get 0 provided k is less than n. So this is the general rule. You should try to prove this using the principle of mathematical induction. And a more general rule can be written in this way: ddt minus a to the power n acting on, say, the signal e to the power at plus t e to the power at plus t square e to the power at plus dot 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 up to, say, t to the power n minus 1 e to the power at. The sum of all these terms may be multiplied by some constants called, say, C0, C1, C2, Cn minus 1, any constants. Then you shall again get 0, because the effect of applying this operator on this sum is same as applying this operator on the individual terms and adding them. Now individual terms being acted by the operator will give 0, so the sum will also be 0. So this is the most general rule you may remember. Or maybe there is a even more generalization. Consider this operator dt minus a1 whole to the power n1, then this multiplied by ddt minus a2 whole to the power n2, and so on. So now we are combining these operators in series, in cascade. That means they will act one after the other. Let me take, say, up to some number p to the power in p. So this is a combination of operators. So that will act, say, on the signal yt. Now if I take yt equal to, say, e to the power a1t, then the result will be 0. Why? Because, as we said, the order of these operations do not matter. So you can operate this first term on this input signal, on this e to the power a1t, and that will result in 0. So you need not apply the other operators because they will give 0 again when acted on 0. Similarly, if you take, say, t to the power k multiplied by e to the power a1t with, call it k1, with k1 less than n1, then also you shall get 0, because this term when acts on this signal it gives 0. Similarly, if you take, say, yt is equal to t to the power say k2 e to the power a2t with k2 this number integer less than n2, this n2, then also you shall get 0. Why? Because you have to operate all these operators one by one on this signal, and the order of operation does not matter. So you can operate ddt minus a2 first, and that will give 0, and so final result will also be 0. So in this way, if you take yt equal to t to the power kp e to the power apt with kp less than np, that will also result in 0. And thus we can say, in general, if yt is a combination of all these, is a sum of all these, like t to the power k1 e to the power a1t plus this term up to this term, say t to the power kp e to the power apt, you can multiply them with some constants c1 cp, this will also result in 0. So if you take yt to be of any of this form, any of these forms, the result of this operation is 0. Okay, so now how many different forms of y you can have which will result in 0? Let us count that. Here you can choose any number for k1 less than n1. So that means you can choose k1 equal to 0, 1, 2 up to n1 minus 1. So that means you have n number of different choices, n different forms or choices for the signal y, which results in 0. Similarly, you could choose k2 to be less than n2, sorry, here it should be n1. Now in this form t to the power k2 e to the power a2t, k2 can be anything from 0 up to n2 minus 1. So you have n2 different choices, and similarly here you shall have np different choices. So the total number of different input signals is equal to n1 plus n2 up to np. Now let us learn another thing. Suppose we have this operator dn dtn plus dn minus 1 dtn minus 1 may be multiplied by a constant bn minus 1 plus other derivative operators like the first derivative multiplied with constant b1 plus b0. Then if this operator acts on yt, it will produce nth derivative of y dny dtn plus bn minus 1 dn minus 1 y dtn minus 1 plus here b1 first derivative y dot plus b0 times y. That is how this operator works. Let me use a shorthand notation to simplify my writing. Let me just write this ddt, this symbol as capital D, and therefore dn dtn, which is nothing but ddt operator acting n times, that I will write as d to the power n. So this complicated operator can be written in a simpler way like d to the power n plus bn minus 1 d to the power n minus 1 b1 d plus b0. Now you see that this operator looks like a polynomial in terms of d, and an nth order polynomial, you know, can always be factorized into n product terms like say d minus a1, d minus a2 up to d minus an. How do we do that? To do that, we will write this polynomial and equate it to 0, and then we will solve this polynomial equation to find the roots or solutions. Say the solutions or roots of this equation are a1, a2 up to an. Then we know we can write this polynomial as a product of d minus a1, d minus a2, d minus an. Definitely some of these roots can be equal. All a1, a2, an need not be distinct. So therefore, in general, we can write this operator as d minus say a1 up to say d minus ap. Some of these roots, some of these solutions can be repetitive. So maybe we have a1 occurring n times, n1 times, ap occurring np times, assuming that some of the roots may be same or repetitive. However, even if they repeat, the total number of roots n1 plus n2 etc. up to np, that should be equal to this order of this operator n. Okay, so given any operator which looks like this, it can always be written in this form, in this product form, or like this way: ddt minus a1 to the power n1, ddt minus a2 to the power n2. Okay, ddt is same as capital D. So let me call this operator 1, then that operator 1 can always be written in the product form as below. So originally we had this operator which when acts on y produces this output. Now if we use this form of the operator instead, then that when acted on y will also produce the same output. Let me copy paste. And then let me go back to what we saw earlier, that this operator will have n number of different signals which gives 0. That is what we said before. This operator has n number of different signals on which this operator gives 0. After this mathematical interlude, it is our time to come back to this system theory. You know, the input-output relationship of many commonly encountered LTI systems have a common form which we call as linear ordinary differential equation with constant coefficients. And this relationship looks like this. Say input x of t is equal to the output yt multiplied with a constant coefficient say b0 plus dy dt multiplied by b1 plus the second derivative of the output and other higher order derivatives, say up to the nth derivative of the output plus some constant times the n minus 1th derivative of the output. So this is the common form of the relationship between the input and output of many common LTI systems. For example, consider an object with mass m on frictionless floor. Input force is xt and output displacement is yt. The relation between the input and output is like this: mass times acceleration is equal to input. This is one example. Another example could be a piece of coil or a pure inductor with inductance L, and if you apply a voltage V of t across it, then the current that will flow through the inductor, call this the output, and the voltage is the input. Then the relation between the input and output is like this: L di dt, derivative of the output, is equal to Vt, that is the input. So in general, x is the input and y is the output, and this is the relation between the input and the output, which we can also write using the notion of operators in this way: dn dtn plus bn minus 1 dn minus 1 dtn minus 1 plus ddt multiplied by b1 plus b0. This operator acting on the output y is equal to the input. In general, the input is known and the output is unknown, or we have to find it out. Now, had it been the other way, if we had input here and output here, it would be very easy to calculate the output from the input. But unfortunately, it is not so. We have output here operated by this operator and input on the right side. So finding the output from the input is slightly difficult. But our task is to find output given the input. Please note that for these types of systems, it is not possible to get the output from the input alone, because if we solve this differential equation, we will get many different solutions for this output y for same input x. For example, say here, consider say xt to be given as 1 constant, and say m is also equal to 1. Then output yt could be equal to half t square plus t multiplied by some constant k1 plus k2. This is the solution for the output given this input. And here k1 and k2 can be any number. K1 and k2 could be any number. That means for all values of k1 and k2, this yt for any value of k1 and k2 will satisfy this given differential equation given the input equal to 1. So there are many possible solutions for the output for same input. However, if I tell you the value of k1 and k2, then the solution or the output will become unique. Please note that k1, this k1 is equal to the value of the output, the derivative of output at t equal to 0, and k2 will be equal to the value of the output at t equal to 0. If these two values are given, if k1 and k2 are given, then output will be uniquely determined. That means if the initial value of the position or displacement and the initial value of the speed or velocity at t equal to 0. If these two values are given, then I can uniquely determine the expression for the output. Otherwise, if you take any value of k1 and k2, that will still solve this given differential equation. So we need to know something extra other than the input to get the output uniquely, like this, in this case, the initial position and initial velocity. So given the system equation and the input, if we want to get the output uniquely, we also need to know something more, what we call as the initial conditions or boundary conditions. These are nothing but the value of the output at, say, time t equal to 0, and say the derivative of the output at t equal to 0. So this is same as ddt of y at t equal to 0. Then the second derivative at t equal to 0. These values should also be given. Now, if this differential equation has an order n, then for getting the unique solution, we shall need n different initial conditions to be given. For example, y0, first derivative, second derivative, up to nth derivative of, sorry, n minus 1th derivative of the output at t equal to 0. Okay, let me repeat. If the order of the differential equation is n, then we need n number of different initial conditions to be given. Then only we can find the output uniquely. Let us understand this fact intuitively. Suppose this is the given equation, and at time t equal to 0, the value of y0 is given, first derivative also given, second derivative also given, up to n minus 1th derivative. These are all given. So values are given at the beginning, and then say after a small time interval at t equal to delta t, we can calculate the value of y at that time using the rule that this is equal to y0 plus the rate of change of y multiplied by delta t. So this value you can calculate. Similarly, the value of the first derivative at delta t, you can calculate it as its previous value at t equal to 0 plus the increment in delta t time, which is delta t multiplied by the second derivative, which is also given. Since this is given, you can also calculate this. In this way, you can calculate all other derivatives at time delta t, like y double dot at delta t, that you can also calculate. However, at this point, if I try to calculate the value of n minus 1th derivative at t equal to delta t, then this is equal to its value previously at t equal to 0 plus the increment delta t multiplied by the next derivative, which is nth derivative at t equal to 0. However, this value is not given. Here, this value is not given. We have only up to n minus 1th derivative. But no problem. This value at t equal to 0 can be calculated from this given equation. How? For that, we will use this system equation, and from this you can write this nth derivative is equal to xt minus all these terms. So keep the nth derivative on the left and bring everything to the right. Now at t equal to 0, y0, y dot 0 up to the nth derivative, all these values are given and input is also known. So at t equal to 0, you can calculate the nth derivative, the value of the nth derivative of y at t equal to 0 from the given input and the given other derivatives or initial conditions. So if I call it equation 1, then in this table, this value can be calculated or can be found from equation 1, and all other values are already given. So these green colored values, green values are given. Nth derivative is not given, but that you can calculate using this equation and the other derivative values which are given. So therefore, at this point, delta t time t equal to delta t, you can calculate this n minus 1th derivative using the nth derivative at t equal to 0. So all these blue values, all values can be calculated. Also, you can calculate the value of the nth derivative from, once again, from equation 1, that is the system equation. So if you start from the known values of output and its n minus 1 derivatives at t equal to 0, you can calculate the value of the output and other derivatives at t equal to delta t. So these values can be calculated. And after that, you repeat the same process for t equal to 2 times delta t. You take these values as known. From that you can calculate the values at next instant. So the conclusion is that if I know the system equation, if I know the input, and if I know n number of initial conditions y0, y dot up to n minus 1th derivative at the time 0, then the value of the output can be calculated in subsequent time instants. So therefore the conclusion is that input plus n number of initial conditions together give me the output uniquely at any point of time after t equal to 0. Now, given the system equation and the input, you can get many yt which will satisfy the differential equation together with the input x. But for a practical physical system, when one input is given, we must get only one output. We cannot have more than one output at the same time. In fact, among the many possible solutions which satisfy the differential equation, only one solution will come out as the output when the input is given. But the question is, which one? That depends on the initial conditions. If one signal yt satisfies both the differential equation together with the input as well as the initial conditions, then that is the one which will come out as the output. This is a very important fact that you must understand. Next, we shall learn a very important fact that these types of systems which follow the differential equation of this form, they are linear and time invariant. Okay, so this type of system where the input and output are related by such a differential equation with constant coefficients, this b0, b1, bn minus 1, they are constants. Then such a system will be linear, time invariant, it will have, in general, it will have memory, it will be causal, but it can be either stable or unstable. Let me justify my claim. Let me start with the linearity. Linearity means it should be homogeneous and it should obey superposition. Of course, under initially relaxed condition. That means under the condition that y0 is equal to 0, y dot 0 equal to 0, and so on up to the n minus 1th derivative at t equal to 0 is equal to 0. So this are the boundary or initial conditions. Now suppose for such a system, when input is x1t, then we got output say y1t, which means what? Which means the signal y1 satisfies this given differential equation with x replaced with x1 and y with y1. Also, it satisfies these initial conditions. So let me write, that means dn dtn of y1 plus all other terms up to b1 dy1 dt plus b0 y1, that should be equal to x1 according to our assumption, and also y1 0 is equal to 0, y1 dot 0 should be equal to 0, and so on. Then suppose when input is x2, then the output that we get is y2. Now this means if you put y2 here in this equation and write dn dtn of y2 plus all other terms up to b0 y2, that will come out to be equal to x2, and also y2 0, that will be 0, y dot 2 0 equal to 0, and so on up to n number of terms. Now if the input is x1 plus x2, sum of previous two inputs, then what will be the output? I claim that output will be y1 plus y2, the previous two outputs. Why this claim is true? Because let us first check whether this y1 plus y2 satisfies the given differential equation or not. So if I put dn dtn, here I put y1 plus y2 plus all other derivatives up to say b1, then ddt acting on y1 plus y2 plus b0 y1 plus y2. This you can write by separating y1 and y2 as this. All y1 terms plus all y2 terms. Now the first set of terms that will give you x1 and the second set of terms gives x2. So this y1 plus y2 together with x1 plus x2 satisfies the given differential equation. And secondly, does it satisfy the initial conditions? Let's check. Y1 plus y2 at t equal to 0 will be equal to y1 at t equal to 0 plus y2 at t equal to 0. Both of them are 0, so this is 0. Similarly, the other derivatives you can check. d dt of this at t equal to 0, this will be y1 dot 0 plus y2 dot 0, and that is also equal to 0. So this also satisfies the initial conditions or boundary conditions. So y1 plus y2 is the signal that satisfies both boundary conditions and the given differential equation. So it has to be the unique solution corresponding to the input x1 plus x2. So y1 plus y2 is the one and only unique possible output for input x1 plus x2. So this obeys superposition principle under, of course, zero initial conditions. You should check yourself that if the initial conditions are not zero, then superposition principle is not going to hold. Next, you check yourself that homogeneity principle is also valid. Homogeneous under zero initial conditions. Check it yourself. This is your homework. So this kind of systems are linear. Let us now check the time invariance. For that, note that starting from zero initial conditions, output will remain 0 as long as input is 0. So if input is 0 and if you start from 0 initial condition, then the output will also be 0 as long as the input is 0. Why? For that, let us go back to this tabular approach of calculating output starting from the initial conditions. Suppose all these initial conditions are 0. Then at the next instant, y delta t will also be 0 because this was 0 and initial derivative is also 0. So at the next moment, output y will also be 0. Similarly, all these derivatives will also be 0 until the last one that we have to check. But you note that this last derivative nth derivative, that will also be 0 because we are calculating this nth derivative from this equation using the input and other derivatives. But input is 0, we said, other derivatives are 0, so nth derivative will also be 0. So as long as input is 0, this derivative will also be 0. And then when you calculate these values at the next time instant, you will get all of them 0. After that you calculate them at next moment, they will also be 0. And they all will remain 0 until and unless this input changes to some non-zero value, they all will remain 0. Okay, so here now if you consider a system, you give some input, arbitrary input starting from t equal to 0 with 0 initial conditions. Call this input x1t. This goes to the system and say the output that you get is like this. Call it y1t. Now, instead of giving this as the input, if you give a different input which is same as before but it is delayed by some time, call it x2, and this is equal to x1t minus some delay, capital T. So this point is capital T. How will the output look like? So we are again starting from 0 initial conditions, and then up to this point input is 0. So output will also remain 0 up to this point t. So output will also be 0 up to this point. And then at this point we still have 0 initial condition because output and all its derivative will remain 0. Okay, so up to this point, and at this point you are getting the input. So the situation is very similar to the previous situation at t equal to 0. So quite clearly now the output will take the same shape starting from this point, and it will look like this. So it will be y2 equal to y1 t minus t. So that's how the system will be time invariant. Now let us talk about causality. Consider the system and consider the input to be an impulse signal occurring at some time t. So this is delta t minus t. This is the input, and how the output will look like. So once again we are starting from 0 initial condition, and as we have just mentioned that If we start from 0 initial condition, then as long as input is 0, output will also remain 0. So the output will also remain 0 up to this point t, because we are starting from 0 initial conditions. And after that you may get something. So this is the impulse response, which is by definition the output of the system when you give a impulse input starting from 0 initial condition. And you see, we find that the impulse response starts after or at the moment when the input is or this impulse is given. If you give this impulse at t equal to 0, then the output will also start from this point. And so this ht, this is not ht, this is ht minus t. So let me write here ht. You observe that ht is equal to 0 for t less than 0. And we have learned that for a LTI system, when this condition holds, that system is causal. In a simpler way, output does not start before you give the input or cause. So the system is causal. Finally, let me talk about the memory. This kind of a system can have memory unless you take the equation to be equal to yt equal to xt with b0 here, and if you take b1, b2, all other coefficients equal to 0, unless you do that, then the system can have memory. In this particular case, we will have no memory because the output depends on the input at that particular instant only. So we will have no memory, but in general we can have memory. For example, if you take b1 equal to non-zero dy dt plus b0 y is equal to x, or let me just take this term only, then this implies that output is equal to integration of x. To be more precise, let me write it this way. Integration of dy dt will be equal to integration of xt by b1 dt, and let me take the limit say equal to 0 to arbitrary time t, 0 to t. Then this implies left hand side will be y at time t minus y0, and right hand side will be the integration of x from 0 to t. So output at time t depends on the input, all input values from 0 to t, including previous inputs. So this has memory.